Hello, welcome back. Now at this moment, we are going to explore how the exception level 0 can be used in Linux operating system. So based on the system architecture, let's review how EL0 can be used, and then we are going to explore how the software can be running at exception level 0. So here is the simple architecture diagram that is based on single operating system. As you can see, the software world is divided into the two worlds. The first world is non-secure world, and another world is the secure world. But most of the software is running in the non-secure world. So in the non-secure world, the Linux application and several applications like YouTube application or Chrome browser application can be running at exception level 0. And in the secure world, the security sensitive application called the trust application can be executed in the secure world. Now let's look at another architecture diagram based on the virtualization environment. The virtualization environment means there are more than two operating systems in the one single system. In this example, there are the multiple operating systems. The operating system in the virtualization environment is called the guest OS. Usual application can be running in each the guest OS. In the guest OS 1, there's usual application running in isolated area, and here is another application that is executable at exception level 0. So based on this virtualization environment, the usual application also running at exception level 0. So now that let's break it down how the exception level 0 can be used in the Linux operating system. So here, this is exception level 0. This is exception level 1. As you know, the usual application like YouTube application or Chrome browser application can be running at exception level 0. For example, most of the application you are using in the smartphone could be the example of user application. Now, important question at this moment is which code can be running in the user application. Here, this is the basic skeleton code for Linux, the system programming. So this is the hello world, the skeleton code. This kind of Linux system programming code can be running at exception level 0. So this is the most simple basic, the code that can be running at exception level 0. Now, so let's focus on the privilege level of exception level 0. The ARM architecture indicates that the exception level 0 is corresponding to the privilege level 0. Sometimes we call EL0 the unprivileged. That means access to hardware resource at exception level 0 is not allowed. But remember that software at exception level 0 can use most of the general purpose register. Then software at exception level 0 can run any of the assembly instruction such as arithmetic assembly instruction or bit shift or bitwise assembly instruction. But remember that some of the assembly instruction to control the hardware resource is not allowed. So here is the 3 example. So user application cannot access to specific instruction, or user application cannot read the value of the system register, or it cannot write the value onto the system register, because those two components, specific instruction and system register, is related to the controlling the hardware resource. And also, direct access to particular memory access is not allowed at exception level 0. Now here is the 2 examples. So assembly instruction, they are not allowed to run at exception level 0. So this is the HVC assembly instruction, and here this is the SMC assembly instruction. This assembly instruction need at least pre-build level 1, running this kind of the HVC and SMC instruction is not allowed. If the software attempt to run this instruction, in this case, ARM core will generate exception. As repeated, this assembly instruction require the pre-build level 1. That means software at exception level 0, that is with the pre-build level 0, cannot run this assembly instruction. Now here is another example to access some specific system register. Remember that most of the general purpose register can be used at exception level 0. But so accessing this kind of system register is not allowed. Here, this is a VBAR EL1 register. This is a ELR EL1 register. So in order to access this kind of system register, software should be running at exception level 1, not exception level 0. So access to this register is related to some controlling the hardware issues. So running assembly instruction to access this kind of system register is not allowed at exception level 0. If software try to access this system register at exception level 0, ARM core will generate exception. Now, software may go through some of the situation to access the hardware resource. Some of the user application wanted to access read the system level information. But in this situation, the user application can use the system core. The system core can be interfaced between exception level 0 and exception level 1. From operating system perspective, system core is interfaced between user space and kernel space. So this system core interface in Linux operating system can be implemented using as a VC assembly instruction. So access to hardware resource is not allowed at exception level 0, but software will need those kind of situation to access hardware resource. Then this should use the system core interface. The system core has the two components. First one is system core number, and the second one is system core handler. The system core is a sort of the standard that is specified in the POSIX standard. So if you refer to the text specification, you're going to find out how to access the particular system resource using the standard IP. Now let's look at another assembly instruction that invoke the system core. Please look at this. In this line, the move assembly instruction can be performed. This value will be copied onto X8 register. So X8 register means this register holds the system core number. This hexadecimal format data can be converted into the decimal format. Here 63 is corresponding to this hexadecimal format data. In other words, 63 is the system core number for read system core operation. So before SVC assembly instruction, the system core number should be specified, and then as you can see, SVC instruction can be executed. When running SVC assembly instruction, core will perform the two tasks at the same time. The first thing is to the branch to the exception vector address that is available at exception level 1, and then at the same time, exception level can switch from EL0 to EL1. This is what the SVC instruction does to implement the system core. But at this stage, after SVC instruction is performed and the controller is moved to exception level 0, then exception handler at exception level 1 will read the value of X8 register to identify the type of system core number, and then corresponding the system core handler will be called as subroutine. So this is how the subroutine can be implemented based on the value of x88 register. In this lecture, we walk through some concept or feature about exception level 0. So exception level 0 is important and component of exception level. The usual application can be running at exception level 0. Then direct access to hardware is not allowed. So in order to access hardware resource, user application should make use of system call. In order to perform system call, add visual assembly instruction, and here is the example for the visual assembly instruction. As you can see, the system call number should be specified before its visual assembly instruction. So here is the key point of exception level 0 in Linux operating system.